This is the background part. Since pandemic situation is getting worse in Hong Kong, people are required to wear a face mask when going outside. It has been proved that wearing a face mask is the most efficient way to avoid COVID-19. Besides, wearing the face mask can also greatly cut down the pandemic spreading. Though it is required to wear the mask when people go to public places, some people still do not follow the rules and take off the mask. This shall be fine. However, it's not possible for the guards to spy on everyone all the time. Therefore, it's necessary to have a monitor that can watch everyone all the time and can automatically detect whether there's someone taking off the mask. If so, just to pick that guy out and punish him. Then it comes to a critical problem: how to detect people whether they are wearing the face mask or not. We introduce you SSD algorithm, which is the object detection algorithm and can run in real time. SSD stands for Single Shot Multiple Box Detector. It's a method for detecting objects in images using a single deep neural network. We apply this algorithm to implement the face mask detection system. Our data comes from alpha dataset and weighted face dataset. Our dataset consists of nearly 8K images and corresponding annotations. There are roughly 4K images from the alpha dataset in which people do not wear the mask, and the rest of the images come from weighted face dataset, have people wearing the mask. Image files are in the format of JPG and annotation files are in the format of XML, where the information of coordinates of face bounding boxes is recorded. Therefore, each image has two types of information: label information and positional information. We may TF records file out of the dataset as input data. Before turning images and XML files into TF records files, SSD also implements a data augmentation. Each training image is randomly sampled by one of the following options. The first is to use the entire original input image. The second one is to sample the patch so that the minimum J-card overlap with the objects is the following numbers. The third one is to randomly sample the patch. The size of each sampled patch is between 0.1 and 1 of the original image size, and the aspect ratio is between 0.5 and 2. SSD also keeps the overlap part of the ground truth box if the center of it is in the sampled patch. After the aforementioned sampling step, each sampled patch is resized to the fixed size. In our experiment, it's 300 by 300, and it's horizontally flipped with a probability of 0.5. In addition, SSD also applies some photometric distortions.
This part is our base model introduction. The base model is VGG16 network model, and based on that, SSD developed its network architecture. Here is the architecture of VGG16 network. And SSD uses VGG as the basic model and made the following modifications. First, convert fully connected layers FC6 and FC7 of VGG16 into 3x3 convolutional layer Conv6 and 1x1 convolutional layer Conv7 respectively. Second, remove FC8 layer. Third, change the pooling layer pool 5 from 2x2 with dread 2 to 3x3 with dread 1. 4. Added the whole algorithm for the purpose of obtaining a denser score mapping. 5. Then more convolutional layers are added to obtain more feature maps for detection. Let us see the picture below. Then is details of SSD. First is multi-scale feature maps for detection. SSD not only obtains feature maps of different scales, but also makes predictions on different feature maps. Different feature maps contain different features, and different features may have different effects on our detection. It's very likely to increase the accuracy of detection, although increasing the amount of calculation. And then is default bounding boxes. It means that there are a series of boxes of fixed size on each cell of each scale of the feature map. Let us take the first feature map with size 38 by 38 as an example. Total number of cells is 1444, and there are 4 default bonding boxes on each cell, which means total number of default bonding boxes is 5776. For all scales of feature maps here, we will finally get 8732 default bonding boxes. The min size and max size of each default box corresponding to each feature map are determined by the following formula. Here M is 6, and we are not going to talk about more details about how to calculate the size of the default boxes. For each default box, 3 category scores and 4 offsites need to be predicted. So if the size of feature map is 38 by 38, then this feature map has a total of 4 by 38 by 38 default boxes. Each bonding box needs to predict 4 coordinate-related values and 3 category probabilities. Then 7 by 4 by 38 by 38 outputs will be generated on the 38 by 38 feature map. For other scales of feature map, it's quite similar, but maybe with different numbers of default boxes on each cell. Next part is chaining process.
This is our chaining process. During the chaining process, in general, one image is sent to the network to obtain all feature maps. For positive example chaining, it's necessary to match the default box with the ground truth box. Successful matching indicates that default box contains a target, but it's far away from a complete target. The ground truth box is still some distance away. The purpose of chaining is to ensure the predicted box classification confidence and at the same time match the predicted box to the ground truth box as much as possible. Let's take a look in details. We send one chaining example to the network, and we get 6 feature maps corresponding to 6 different convolutional layers. Their names are given below. Then we have nearly 9k default boxes out of these 6 feature maps. Among all these default boxes, we compute following outcomes: classification confidence with respect to every class, and the 4 offset relative to corresponding default box. Well, having the results, how do we actually train the network? Are all outcomes of all default boxes useful? No. We compute each box's IOU score with the ground truth box. We only mark those with IOU score greater equal to 0.5 as positive example in terms of the classification task, and naturally the rest of them are negative examples. However, this will cause a problem that introduces a significant imbalance between the positive and negative chaining examples, especially when the number of default boxes are large, which typically is the case. Therefore, instead of using all negative examples, it's a good idea to sort them using the highest confidence loss for each default box and pick the top one so that the ratio between negatives and positives is almost at 3:1. Then we only keep those boxes for chaining and calculate their confidence loss. As for localization tasks, SSD performs the regression on each predicted boxes produced by remaining default boxes. Then to calculate localization loss, we can see the details below. The SSD chaining objective is to minimize the total loss, which is the weighted sum of the localization loss and the confidence loss. Before looking at the formula, we should know that there's an indicator for matching the I's default box to the J's ground truth box for category P. The overall objective function is shown below, where the capital N is the number of positive default boxes. If n is equal to 0, we set the loss to 0. The localization loss is the smooth L1 loss between the predicted box and the ground truth box parameters. Plus, SSD regresses to offsets of the ground truth box for the center of the default box and for its width and height. We can see the formula below. The confidence loss is the softmax loss over multiple classes confidences. We can see the formula below. And the weight term alpha is set to 1 by cross-validation according to the paper. By the way, here is what smooth L1 loss looks like.
This part is about pros and cons of SSD. First is the pros. First, the running speed can be fast as YOLO, and the detection accuracy can be great as faster RCNN. And SSD is effective for detecting objects with different aspect ratios. This is because the algorithm uses multiple aspect ratio default boxes for each feature map cell. Second, its cons. It needs to manually set the mean size, max size, and aspect ratio values of the prior box. The basic size and shape of the prior box in the network cannot be obtained directly through learning. The size and shape of the prior box used by each layer of the feature in the network are exactly different, which leads to the debugging process is very dependent on experience. And this part is about our experimental results. First is our prediction. After training the model for 25,689 steps with batch size of 5, we get our final model and use it for the prediction. Although we train more training steps such as 8,000 steps, it's not as good as the one we choose. Just as shown below, we input an image, then it will be pre-processed and fed into the net. The prediction process is quite similar as the training process. However, after getting the prediction of total default bounding boxes, it's necessary to do a selection according to the confidence of the classification. Plus, non-maximum suppression is effectively applied to find the best target bounding box and eliminate redundant bounding boxes. So now we have the output shown below. Next part is our results. Our goal is to detect whether a person wears a mask, and here we'll show more outputs of our experiment. Here is our corresponding results on images, and then is our corresponding results on the camera. It's obvious that our demo can handle the pictures with clear objections with face or mask just as the results we shown before. However, there's still a huge space for us to improve the model. First is the limitation of training sets. A larger training set containing more variable pictures with people with or without mask may take improvement on the model. Second, when the detection targets in the picture increases, the prediction will be worse. It may result from the limitation of our network with input image size 300 by 300 or training samples are not sufficient enough. This project shows how to detect people whether wearing the mask or not using SSD algorithm. Although we get a comparable good model for detecting now, it's still a lot of work to do to improve it. We really benefited from the project and enjoyed the whole learning process. Thank you very much. That's all.